There we go. Let's go. All right, we should be all set, ready to go. Correct? Correctamundo. Let's see. Mathematics review and practice, arithmetic, 8-11-26. Very good. All right, and over here, let's go ahead and check again. Go home. There we go. Arithmetic. Let me go ahead and check the sound. Correctamundo. All right. Now we're set. Hey everybody. So today is August 11th, 2026, and as the title card says, this is an arithmetic review. So what are we doing here? We're actually doing something. It's a little different. It's a little strange, I'll tell you that. And what the concept is the idea that as you read information, you are supposed to have some sort of response to it. And that response can be as simple as 1 to 2 sentences, but every piece of information requires you to have some sort of response, and that shows that you've acquired it. And then a little bit later, once we've acquired the information, then we categorize it. And then once we've categorized the information, then we engage in the recall of the process. So what is the purpose of this stream? The purpose of this stream is to demonstrate. The purpose of this stream is to demonstrate the methods of recall. First and foremost, it's to give me practice to teach in a digital framework. But in addition to teaching in the digital framework, I'm also engaging in some ideas regarding the way we work with knowledge, okay? So in this little diagram that I have here to one side, we have knowledge work is in the center, knowledge work is in the center, and knowledge work is the process, it's the cycle of acquisition, categorization, and recall. Acquisition, categorization, and recall. Those three are what make knowledge work possible, okay? So the purpose of this stream is to put this idea into practice. It is to put this idea into practice, okay? So right now we're doing the acquiring, and then categorizing would follow, and then finally recall follows after that. Now, granted, the purpose of these streams is really to help me with the recall, and so you'll see that it's very boring. It's not really enjoyable, I'll give you that, but it is necessary. It's a necessary part of the training in order to become more cognizant of what I'm supposed to be doing as a teacher, which is my profession that I am advocating for, I guess you'd say. So now let's go ahead and move forward. I'm currently, as my text that I am working through, I'm not doing copy work of the text, but I am doing a read-through of Augustus de Morgan's Elements of Arithmetic. So he was a famous mathematician who lived in the 19th century, and he wrote this very good textbook on arithmetic. Okay? I know that for a lot of you this is going to be a review. That's why it's labeled as a review. But you probably haven't necessarily seen arithmetic dealt with in this way, kind of a unique and non-direct way of getting at arithmetic, and definitely something that you would not expect a youngster to have to engage with in this way. I would never. Oh, that'd be so sad. I would never ask a grade school student to consider the information in this way. But this is essentially the concept of, if I have to do a review of arithmetic as part of my training for becoming a math teacher, then I might as well look at arithmetic with the lens that I have, which is someone who has lived a few years longer than a grade schooler, hopefully, and has the ability to perceive the forms, perceive the ideas that underlie. So I'm looking for insight and understanding, okay? So now let's go ahead and get started. So what I have here is, according to the idea of, once again, if we're looking at this little layout right here, the idea is the acquisition leads to categorization, which then leads to recall. And essentially what we're doing here with reading through the book is we are acquiring the information, okay? We are acquiring the information by simply reading the book. And then what I'm doing here with this, what looks like strange cryptic text over here, this is what is known as shorthand. This is known as shorthand. Let's go ahead and write that out here. This is shorthand, okay? I don't expect you to know what this means, and I barely know myself, but what it is a type of writing that enables you to capture information more quickly and more readily in a shorter amount of time, okay? So this is shorthand. So what I have here is the precursor. This is the precursor to the categorization of information, okay? This right here is the precursor to categorization. It's an idea, and I will go ahead and read through it for you as a bit of review before we continue. And this says that every position in the linked system of numeration is given a name. The first position bears the name of the unit's place, and every successive position is given the name of the associated fact, or of the associated factor. This should be factor, okay? Of the associated, let's not make it purple, let's make it, there we go, of the associated factor. All right? This is the idea that I want to derive from this particular paragraph of Augustus de Morgan. Can you see if I move my mouse over? I need to make sure that you can see the mouse moving over on the page, because if not, I might need to use the underliner, highlight text. There we go. So can we underline here? Oh, stop. Don't move. Oh, stop moving. There we go. Ah, hey. The text does not want to do what it's supposed to do. So if can we highlight? No, we can't. Undo. There we go. Whatever. So anyway, we're looking at paragraph 3, Roman numeral number 3, okay? And it says that the right-hand figure is said to be in the units place, and next to that is the tens place, the thirds place, or the third is the hundreds place, and so on. So the big idea that I want to derive from that sentence is that every position, so it's like the meta idea. Every position in the linked system of numeration, which is what we're talking about here, is given a name. That's the key. Every one of them bears a name. The first position, and that is the right-hand figure, the first position bears the name of the units place, okay? That's the one that's key, is that it has the name of the unit. And every successive position is given the name of the associated factor, And that's key because if you read through paragraph 3 of not Euclid, Augustus de Morgan, then you see that every position bears the name of the factor. There's the tens factor, the hundreds factor, the thousands factor, the 10,000s factor, the 100,000s factor, so on and so forth. Okay? So that is the takeaway from the number 3, and that would be the fleeting note. Now, what I would do is if I had to give an example to someone, then let's go ahead and lay that out. I'm going to say that this is A, right? So A, we can use letters here, A, B, C, D, E, and so on and so forth, okay? So over here, I would say A is the units place. So I would make a little name for myself, right? A is units, B is tens, C is hundreds, right? so on and so forth, okay? Dot, dot, dot. All right, so there we go. That is the takeaway from paragraph number 3. And now paragraph number 4, when a number is itself an exact number of tens, hundreds, or thousands, etc., as many ciphers may be placed on the right of it as will bring the number into the place which it is intended for. The following are examples, and then it gives tens or 5 tens, 50, 700 is 50 or 5 tens is 50, cipher, hence the cipher. 700 is 7 cipher cipher or 00. So what 0 means is cipher. 528,000 is 528 cipher cipher cipher. Okay? If it were not for the ciphers, these numbers would be mistaken for 5, 7, and 528. So what's the takeaway there? And this one is going to be the fleeting note for Roman numeral number 4. So over here, I do Roman numeral number 4, and I'm going to go ahead and start just calling this F-in for fleeting note. The F-in for the fleeting note. And now, once again, I have to go back to my Gregg shorthand. Be advised that the Gregg shorthand is extremely slow, and I do write I start on this side, and I work over to the left-hand side. So I start on the right side and work to the left. The reason for that is because I am left-handed, and shorthand is designed to be as efficient as possible. So therefore, you write in the direction that is most comfortable for your hand. So before I make the note, I'm going to go ahead and grab a little bit of water. So what's the takeaway? The takeaway that I want to put here in Gregg is that positionality is the what's the word I want to look for? Positionality is the ultimate consideration, okay? So I'm going to say in linked numeration, so because once again, remember, the big takeaway from this chapter and really the fundamental concept is the fact that we're dealing with linked numeration, linked numbers, okay? So that's the point I always want to drive home in any of the fleeting notes, okay? So in linked numeration, and for numeration we might have to look it up again, but I'll do what I can. Numeration, let's see if that, oh no, it has an R and then a shun, right? So in linked numeration, there we go. Yep. So in linked numeration, positionality is absolutely essential. Positionality is of utmost importance, And so let's go ahead and look up utmost. So I have my dictionary pulled up over here. You can see me using. There's a link down below. If you're interested, if anyone is interested in practicing shorthand, in learning shorthand, then by all means you can take a look down below and see how it is supposed to be used, okay? Lots of good resources down there. So positionality is of utmost. So I need to look up utmost. And so let's see what the form is there. And that is utmost, okay? Is of utmost importance. Okay? Is of utmost importance. Like so. All right? And we'll do a colon. In order to, symbols, so the word that we want to use there is a symbol known as a cipher. Symbol known as a cipher. A symbol known as, and then we have to check and see if cipher is in the dictionary. So we'll put it, I'll put what I think it is. A symbol known as a cipher. So let's go ahead and check that out. So if we take a look at cipher, we see indeed that there is the word for cipher. Okay, so what I'm going to do is we're going to straighten it out just a hair. So that's cipher. And what I need to do is I need to underline. I need to underline the word cipher. Oh, undo. Don't we have underliner? No, that's the eraser, pen, textured marker. I guess not. So we'll just underline, okay? So a symbol known as a cipher. A symbol known as a cipher is needed to, which means nothing. So we'll change this back and we'll go to comma. A symbol known as a cipher which has no inherent value, which has no inherent value. No inherent value. Okay. No inherent value. So we need to look up inherent. Let's see, what would inherent be? It would be inherent, like that. Let's go ahead and see if inherent is one of the words. It is, and it uses a backwards R principle, so that's nice. We'll go ahead and add that in. So this is inherent. There we go, a little bit bigger. And I'm going to make this, yeah, because the medium's a little too big. Maybe a 3. Maybe we need to have this at a 3, level 3 for our pencil. Let's see what 3 does over here. So yeah, that's better. Yeah, come on. Like I said, this is very, very difficult and very, very time consuming, which is why if I put in the time now, when no one watches, then that means that when the time comes when people should be watching or when it's actually useful, I will have ironed out all of the bugs. At least that's the hope. That's the dream. I can't speak for it fully. Oh, come on. Let's go. Oh, oi, oi. It's doing a backwards R, and I don't like it. Come on. Undo. There. It's like trying to make a character jump, and the physics are all wrong. All right, well, that's good enough. So that's inherent. So no inherent. So let's go ahead and jump back here. What is this? We have, it is called a cipher, which has no inherent value. It has no inherent value. All right. So let's read back what we have so far. We have in linked numeration, positionality is of utmost importance. Symbols, a symbol known as a cipher, which has no inherent value in itself, must be used to shift values, to shift symbols that do have value, to shift symbols that do possess value. Let's see, possess is going to be POSS, I believe. Does it just curve back in on itself? Let's see. if this is POSS and then it curves down, let's see if that's correct. Possess, we scroll up, and that it is somewhat correct. The S needs to be fixed just a little bit, so let's go ahead and curve down. So this is possess. That do possess, and if that's a do, then that needs to be a little longer. Okay? Symbols that do possess value are listed in their correct position. Are listed in their correct position. In their correct positions, okay? So let's go ahead and read back over this line and let's see what it says. So in linked numeration, positionality is of utmost importance. A symbol known as a cipher, which has no inherent value in itself, and itself needs, I just realized that that is a double S, in itself, oh, come on. There we go. In itself must be used to shift, and shift needs a T, to shift symbols that do, and I'm going to underline do so that we can really focus on that one, because this is the idea of a cipher has no value, but it's necessary to shift values that do have or symbols that do have value to their correct position so that the number can be accurately shown. Okay, so let's go back here. That do possess value are listed in their correct positions. So I'll read that again. In linked numeration, positionality is of utmost importance. A symbol known as a cipher, which has no inherent value in itself, must be used to shift, and let me check shift. Like I said, I don't apologize. I don't apologize for what I'm doing, because what I'm doing is my own study. So it looks silly and it looks a little bit OCD, but after all, I guess all of us can be a little silly every once in a while. So there's shift, okay? So shift, and I want to clean it up just a little bit. Come on, go into De Morgan. There we go. It's a fun name, De Morgan. And let's go ahead and switch over to our pen, make sure that we're in the correct, to shift. All right, to shift symbols. All right, let's go zoom out so we can see the whole line. All right, here we go. So we have our underliner. To shift symbols that do possess value are listed in, so to shift symbols that do possess value and list them, let's make this a correct sentence, and list them in their correct positions. List them in their correct positions. All right, that's the takeaway idea. That's the takeaway idea. Okay, so now with that out of the way, we might want to give some examples, right? So let's go ahead and list one word, and that'll give us enough. That'll give us enough material. Okay. So example. listed below. And the example does not have to be in shorthand, right? Because it's not a fleeting note. It's merely an example. So the example would be something like 5,000. 5, and we'll actually list the word. So the example would be 5,000. All right? So in order to show this number, we need how many ciphers? We need 2, or we need 3 ciphers, right? So to show 5,000, use 3 ciphers and 1 number and 1 symbol of value. Symbol of value. Okay, so to do that, we first list, we have to shift our number over, correct? So we start first with the cipher. In 5,000, there's nothing in the units place, so we have to drop a 0. There's nothing in the tens place, so we drop a 0, a cipher, and there's nothing in the hundreds place, so we drop a cipher. Notice we're starting from the right hand and working our way over, and then finally, now we have our tens, we have our units, tens, hundreds, and now in our thousands, now we put our value of 5,000. And that gives us our correct, that gives us the correct value. Notice, 3 ciphers. A cipher has no inherent value. It is merely a position holder. And then we have to put the number in the correct position. All right, so that is the takeaway from section from Roman numeral number 4, Now we shift over to number 5, and we go ahead and list that. So here's number 5, and we take a look. A cipher in the middle of a number becomes necessary when any of the denominations is wanting. Thus, 20,006 is 2006, 206 is 206. Ciphers might be placed at the beginning of a number, but they would have no meaning. Thus, 026 is the same as 26, since the cipher merely shows that there are no hundreds, which is evident from the number itself. Okay? The takeaway from that point, a cipher in the middle of a number becomes necessary when any of the denominations is wanting. So what we're going to say is ciphers are used anytime the takeaway is going to be ciphers are written anytime a position bears no value. Anytime a position possesses no value. Possesses. So let's go possesses, and we add another S after that. No value. There we go. So the takeaway from here is that a ciphers are used, or ciphers are written. Let's read back through. Ciphers are written anytime a position possesses no value. A position possesses no value. And by possesses, I mean that there's no number to be written there. So ciphers are written anytime a position possesses no value. Okay? The other takeaway would be, but leading positions do not need to be listed. Okay? But leading positions do not need to be listed. That's the takeaway from number 5, okay? So ciphers are written anytime a position possesses no value, but leading leading positions do not need to be listed. And that's it. So that's our takeaway from number 5. And then 26 is 26 is merely an example. If you take so you see how paragraph 20 is just an example, which we will work out in another video. I'm not showing examples in this particular stream. Right now, we're just looking at understanding. We're just looking at the ideas. Later in another video, in follow-up exercise videos, I will work through these examples, but the purpose of this stream is just review. Just review and practice writing functional notes or fleeting notes, okay? Now, we can skip past all of the exercises for 21. We can skip past 22. Oh, okay. So now let's go ahead and see. Let's look at paragraph number 22. So we just did review, and now we're going to do 22. 22. You now see that the convenience of our method of numeration arises from a few simple signs being made to change their value as they change the column in which they are placed. The same advantages or the same advantage arises from counting in a similar way all the articles which are used in everyday life. For example, we count money by dividing it into pounds, shillings, and pence, of which a shilling is 12 pence and a pound 20 shillings or 240 pence. Now, of course, this was written in England, so they are going to be using a different denomination of money than what we would be using, which is dollars and cents, right? Dollars, nickels, dimes, quarters, all that. So that's why the language is a little different, but we could easily make the same comparison to the American system of money, right? So we have numbers of pounds, shillings, and pence. We would say dollars, quarters, and pennies, I believe, generally placing points between the columns. Thus, 263 pence would not be written as 263, but 1 pound, one, and then ... where pound shows that the 1 is in the first column in a pound. Here is a system of numeration in which a number of the second column on the right means 12 times as much as the first same number in the first, and 1 in the third column is 20 times as great as the same in the second, or 240 times as great as the same in the first. In each of the tables of measures which you will hereafter meet with, you will see a separate system of numeration, but the methods of calculation for all will be the same. Okay, so he's just saying that there will be separate systems of numeration where each one is slightly different. Okay, that's essentially all that is being located. All right. I don't know if there's really. Let's see. Could we take a fleeting note away from 22? Our method of numeration arises from a few simple signs made to change their value as they change the column in which they are placed. For example, we count money, thus 263 pence would not be written as 263, but as 1 ... where pound shows that the I in the first column is the pound. Here is a system of numeration in which, a number in the second column on the right means 12 times. A number in the second column on the right means 12 times as much as the same number in the first, and 1 in the third column is 20 times as great as the same in the second, or 240 times as great as the same in the first. So the takeaway from here is that when we're talking about British money, and for this, I'm going to have to work out an example below. So this isn't really a fleeting note because this isn't a concept. This is just showing us how British money works, how British money systems are used. So It's not really necessary to consider that. It's not really necessary to consider at all. The takeaway for us in shorthand would be the takeaway would be modified versions of numeration of the system of numeration. Yeah, so modified systems or modified versions of numeration are used in different applications, in different real-world applications. So we would say modified, and modified is, let's go ahead and write that here. This is mod, I think that's modified, but let's go ahead and check it. So we go over here, we check modified, modify, and we look for our Gregg shorthand symbol, and that's modify, okay? So it's modify, so it uses a DF stroke. So we go modified systems, or modified forms. Modified forms of numeration are used in many real-world applications. Are used in many real-world, so that one is real and hyphenated, real-world applications. And this is going to be applications, I believe. So let's go ahead and check that out. Scroll down a little. Yes, that is applications. So in many real-world applications, each, and then comma, we would say each becomes its own system of numeration, its own system of, and system should be just a little bit, there we go, it's like a sideways tilde, should be its own system of numeration, okay? And we have to underline system of numeration because it is a keyword, all right? So let's go ahead and underline that here. This is system of numeration, okay? So that is our takeaway. That is our takeaway from chapter, or from paragraph 22. Even though, yeah, it's a fairly long paragraph, and it's giving the example about money, okay, which now below I might talk about the British system. But here, notice this one of the last sentences. It says, here is a system of numeration in which a number in the second column on the right means 12 times as much as the same number in the first, and one in the third column is 20 times as great as the same in the second, or 240 times as great as the same in the first. In each of the table of measures which you will hereafter meet with, you will see a separate system of numeration, but the methods of calculation for all will be the same. So for us, what that means is that we will take a look at the the British system, which he was just talking about, and that is the layout in this order. So now we're going to switch back to normal view, and we're going to put our pound sign here, which is shaped like that. It's a libre, or libra, which is the Roman word for pound, shaped like that. And we have our ith value, or our I, is located here, followed by a dot, and then we have another value, another I here, and then we have a dot followed by two I's right here. Okay, so this shows where I shows that the I in the first column is a pound, and so that one is right here. This one would be a pound located at that point. And then the ones that follow after are shillings and pence. So this is shillings. In fact, what we'll do is we'll just put this here. This one is a pound. This would be shillings. And this would be pence. Now, obviously, we in America, this is not really necessary for us, so I'm not going to spend too much time on the system, but it does give us an interesting opportunity to look at the way that a system of numeration is going to be slightly different. Here in America, of course, and I'm going to lay that down below. Below this example, you'll see that we use all base 10 in our money, whereas in Britain they use a slightly different method, which is here is a system of numeration in which a number in the second column on the right means 12 times as much as the same number in the first, and the one in the third column is 20 times as great as the same in the second, or 240 times as great as the same in the first. So, in this instance, a pound is equal to 240 pence. 240 pence is essentially what we're talking about. Okay? A pound is worth 240 pence, and a pound is worth, if I'm understanding this correctly, then a pound is worth 12 shillings, right? A pound is worth 12 shillings. Let's see if that's correct. Gonna go over here and do a quick Google search and say, is a pound 12 shillings? And it's going to say, no, 1 British pound was equal to 20 shillings, not 12. Okay, 1 shilling is 12 pence. That's what it is. Okay, so we'll go back over here, and I had it miswritten. So 1 pound was 240 pence, and 1 pound had 20 shillings. 20 shillings, okay? 20 shillings made up 1 pound, okay? And so this means that this is 1 unit. This one, there are 20 of these, 20 shillings, and there are going to be 12 pence. 12 pence, 20 shillings, and then 1 pound, okay? So that's how it worked. So this positionality, this is where it's interesting. This is why earlier in the stream I was talking about how positionality, the number of units that can be housed in that position, determines the when you pass off the value to the next location. Okay? So in this instance, a pound is 240 shillings, and a pound is also 20 shillings, and a shilling, 1 shilling, was equal to 12 pence. Okay? A pound was 240 pence, a pound was 20 shillings, 1 shilling was equal to 12 pence, okay? Now it says the UK stopped using this system in 1971, so it has changed, but a lot of the books from the past, and this book was written in 1860, are still going to possess some of the same concepts, or some of the older concepts, okay? So here is a system of numeration in which a number in the second column on the right means 12 times as much as the same on the first, okay? And the one in the third column is 20 times as great as the same in the second, or 240 times as great as the same in the first, okay? So remember this, pound 240 pence, pound is 20 shillings, and 1 shilling is 20 pence. So it's different from the way we do money in the United States, okay? So let's take a look at the way that we use money in the United States. So this is the British method. Let's go ahead and make a little note here. this is the Old British method. This is the Old British method, where it's a pound, shilling, and pence. Okay, 1 pound was 240 pence, 1 pound was 20 shillings, 1 shilling is 12 pence. Okay, and that's the Old British method. Now let's take a look at the American method. So we're going to change color here. Let's go back to the original, and we're going to call this United States currency. Okay, United States currency. Just to put things in context, right? So in the United States currency, first of all, we use a different symbol. We use the dollar sign, the dollar, the almighty dollar. And then we'll use X here, okay? And then we use a single dot, and then we'll use Y here, and then we have Z here, okay? X, Y, and Z, okay? So X equals 100Z, right? And X also equals, because it'd be 100Z, it equals, this would be 10, right? It equals 10Y of that position. If we were to use that, that would be dimes, right? And so what are we going to say here? So X is a dollar. And Z is pennies. Y is also pennies. It's just different variations of pennies. So therefore, we're going to do Y. Y would be it could be dimes, right? It could be tens of pennies. Tens of pennies. Or dimes. Okay? So, in this layout, X is a dollar, Z is pennies, and Y is tens of pennies or dimes. Tens of pennies or dimes. Okay? So, that's pretty much all that we need to take away from 22. And then in 23, in order to make the language of arithmetic shorter, some other signs are used. They are as follows, okay? So, let's go ahead and start building out our fleeting note for 23. So our takeaway from 23, the first one is, the first idea is special names for operations, for, let's see. Some other signs are used. And what is he going to talk about? Difference, and then he has multiplication and division. So certain to reduce the wording, or to make the language. So to reduce the wording of arithmetic, here we go. To reduce the language, or to reduce the wording for arithmetic operations, And let's go ahead and look up the word for arithmetic. So that would be, I'm thinking AR, it's going to be AR, arithmetic. I don't think that's correct, but we'll go ahead and check it out in the dictionary. There's arithmetic, and it's actually easier. It's arith, okay? So we can go ahead and erase that, and we'll go ahead and do arithmetic, okay? So arithmetic. There, come on. There we go. So arithmetic. To reduce, so we have to reduce the wording in the wording for arithmetic operations. For arithmetic operations. So for this we do for, and then there's arithmetical. So we're going to do arithmetic for arithmetic, or I think we can just, yeah, it's just the word arithmetic. Arithmetic operations. Arithmetical, it would be arithmetical. So we have to do arithmetical. Operations is going to be OPR shun, right? Or I think it might just be PR. No, it is OPR shuns, I believe. Let's go ahead and check that. No, it needs the Asian, okay? So we'll do that here. We go OPR shuns. For arithmetic operations, so to reduce the wording for arithmetic operations, certain key symbols symbols are used for the symbols are used to denote. Symbols are used to denote. Let's look up the word denote. Denote. What is denote? There is denote. So symbols are used to denote the processes. The processes. Processes. Is that correct? It's like a process. Yes, pretty much. Yes, okay, good. All right, so certain symbols to reduce the wording for arithmetic operations, symbols are used to denote the processes. And then what we'll do is we will then list those processes below. So those processes are as follows. So in this first, if you see here, this is 23.23 and then the ith value, 23 and the ith value. 15 and 38 means that 38 is being added to 15 and is the same thing as 53. This is the sum of 58 and 38 and is read 15 plus 38. Plus is the Latin word for more. So here what we're going to do is we're simply going to lay out the forms. So the sum, or let's see, when two numbers are joined, let's go ahead and do this here. So the first one, this is the first value, this is I. When two numbers are joined, when two or more quantities, let's do quantity, okay? So let's look up quantity. Oh, I think I know that one, but I'll check it. Quantity. If I could spell it correctly. Here we go. Quantity. There we go. So there's quantity. If two or more quantities are joined, like so. I think that's join, but let's go ahead and check that. No, that'd be joined. Oh, good grief. Join. There's join. Okay. If two or more quantities are joined, the result is called the sum. The result is called the sum. So we go the no, that is not correct. Result does not use an E. The result, it's resu. There we go. The result is called the sum. Is called the sum. And I'm going to underline that because it's italicized in the book. And for italicization, we show that using underlining, okay? The result is called the sum, okay? And the special symbol, so that's the end of the sentence there for sum. And then the second part of the sentence for this fleeting note, so remember this is what we're creating, is a concept that would then be placed in some sort of note-taking paradigm, okay? But this is the fleeting concept. So when two or more quantities are joined, the result is called the sum. The symbol of joining, the symbol, he doesn't use addition here, which is interesting. I wonder why he doesn't use the wording for addition, but it doesn't matter. I'm going to use it here. So I'm going to say that the symbol of addition, the symbol of addition is the cross, I guess you'd say is the cross of addition, is known as the plus sign, is known as, it's known, oh, let's see, this is known as plus. So let's do plus. This is P-L-U-S, right? It's known as plus. And yep, that is plus. It's known as plus. And we're going to underline plus. All right? It is known as plus and is denoted by by the character of, and then in parentheses we then do the symbol of plus, the plus symbol, right? So let's see if that's correct. So when two or more quantities are joined, the result is called the sum. The symbol of addition is known as plus and is denoted by the character of, and then in parentheses we then have that value, is denoted by the character of the plus symbol. And let's go ahead and underline the plus symbol in order to then show it correctly. So that is the plus. That's the plus symbol, okay? Now, I am going to make a quick note in here that plus is the Latin for more, okay? So I'm going to do another parenthesis below, and we're going to show that plus is the Latin, is the, and then he has, capital L Latin, so we're going to do that here. I think this is L Latin. is the Latin for more, for more. And more is underlined as well to show that it is, well, this is tricky because underlining makes it capital in Gregg, but if we do maybe 3 could do, we'll use that for underlining. Okay, so there we go. Plus is the Latin for more. All right, so that is the first paragraph. That's our first point. And now we do our second one for the second symbol. So remember, these are the symbols which are going to increase the brevity. They increase the brevity for the language of arithmetic. All right? So what's the second one? He gives an example, 62. 62 minus, or that symbol, 12, means that 12 is to be taken away from 64 and is the same thing as 52. This is the difference of 64 and 12 and is read 64 minus 12. Minus is the Latin for less. Minus is the Latin for less. So what are we going to do here? We're going to do the same process, which is, we're going to say when one number is taken away, or when one quantity is taken away from another quantity. So we have when a quantity is removed from another quantity. When a quantity is removed, and removed is I think that's removed. Let's go check that out. Oh. Let's go back down to, not our note, we need our dictionary. There we go. So when one quantity is removed, I got to go back up to where I was, which is wow, he goes full bore early. That's really neat. Page 17, we've already gone over that. He has the tables to show how to do. Wow. I think I'm gonna like the rest of I'm gonna like the rest of De Morgan for sure, because he's digging into the ideas of arithmetic really well. Really well. I love it. Okay. So we have the difference, right? So when a quantity is removed from another quantity, the remainder, or the value that is left, the value that is left let's see if that's left. Yep. The value that is left, and it's just LFT, is known as the difference. And we're going to underline difference. Okay, there we go. We've underlined difference as the difference. Okay, and the symbol used to denote the operation, to Once again, denote works well because it really ties it in. To denote or show, we can use denote or show for there. To denote or show the operation is called minus, So the symbol used to denote or show the operation of subtraction, to show the operation of, and then we'll do subtraction. So let's go ahead and do subtraction, which is going to be down here. Okay. Is called minus. And we have to do minus would be minus, because we've done plus and then we have minus. So let's check minus. Minus. Okay, so let's go ahead and fix that up a little bit. Minus is called minus. So the operation of subtraction is called minus and is read as and is read as, and then quote, little quote symbols, x minus y, x minus y, in fact, is read as. Then here, what we do is we switch back. So anytime we have a math operation, we show it here, x minus y. This would be read as, now we switch back to shorthand, is read as x, and for x we could just do ex, right? X minus y. And y is, of course, that, x minus y. It is read as x minus y. We'll actually put this here in the center. X minus y is read as x minus y. There we go. Okay, so that's it. That would be our note for number 3, or for number 2. Okay, so let's go ahead and go back over here. I need to go ahead and fix up the video capture. It's a little too dark, so let's go ahead and bump up the levels just a hair. Bump up the gain. There we go. Yeah, it's all right. Okay. Back to work. Back to work we go. Okay, so let's go over here. And that's it. So let's just keep on chugging. So x minus y. All right, and that would be the Gregg shorthand approach. Okay, the Gregg shorthand approach. Now we have x minus y, and what's our next point? So let's go ahead and minimize this screen here. There we go. I have to use the mouse for that. All right. So here's our next one, which is number 3. Okay, here's our third consideration. And each of these would have to then fit on the cards, so we have to make them nice and easy and short. So here's our next fleeting note. 9 times 8 means that 8 is to be taken 9 times and is the same thing as 72. This is the product of 9 and 8 and is read 9 into 8. Now that's an interesting way of saying it. 9 into 8. Okay? So let's go ahead and take a look at that. Is to be taken when a number, so here we go, here's when a number is taken a certain number of times, a certain number of iterations, we'll say a certain number of iterations. A certain, I think I'm going to do quantity here. When a quantity, there we go. When a quantity is taken a certain number of times, a certain number of times, the result is called the product, is called the product, and the operation is denoted thus, is denoted thus. Okay, I need to go ahead and make sure that thus is correct. Oh, that's thus. Okay. Glad I checked. Is denoted come on. There we go. Is denoted thus. And then below we switch back over to the regular way, so we would have A, and then the symbol, A, symbol B, and it would be read as A, which is here, right? This is A into B. A into B. Okay, so I'm going to underline this, or I'm going to box this in to show that it's separate. A times B, and it's read as A into B. A into B. Okay? And that is also known as the multiplication symbol. It's known as the multiplication sign. And I'm going to make that note under here. So the X symbol is known as the multiplication sign, and multiplication, I believe, is multiplication. So let's go check that. Almost PL, and then we have to have the K. So we're going to go multiplication. We go multiplication sign. And we're going to go ahead and underline this. I know this is not from De Morgan, but I'm going to go ahead and leave it in. It's 9 into X. So here, like 9 into 8 in number 3, as you see that, it would be 9 into 8, and is read 9 into 8, okay? But here it would be X into B, or A into B, A into B, okay? Once we get to 4, then I'm going to read back. So far we have covered 1, we've covered 2, we've covered 3, and now we're covering the 4th one. So let's go ahead and write the quick note for 4. And this one is, that's 3. So, oh boy, this is tricky. I'm going to have to switch the order since we're backwards. This is 4. Okay? I know this is wrong Latin. I know it's not, I know that's not the way it is, but we're reading it from the right-hand side over, so I guess if we're going to be weird, we're going to be weird together. So this is 4. 108 over 6 means that 108 is to be divided by 6, or that you must find out how many 6s there are in 108, and is the same as 18. This is the quotient of 108 and 6, and is read 108 by 6. Okay, so here we say when you attempt to find how many of a number is in another number, so once again, when you attempt to find, let me check find. Yep. When you attempt to find how many of a number, of one number, of one number is in another number, you find how many times a number is in another number. This is called division, right? This is called division. And for division, I need to look that up. So this is called division. Here we go. There's division. Comma. And the resulting number, right? So we have when an amount, that should be here. When an amount to, when you attempt to find how many of one number, let's go ahead and underline this here, of one number is in another number, this is called division. And let's make division just a little bigger here so that it's separated from this. So we have is called division. Is called division. All right. This number is called division, or the process. This is called division, and the result, comma, and the resultant's number, or actually, we'll just do the result of the operation, is called the quotient. Now, quotient is a word I don't know what it looks like in Gregg, so we'll check it. Is called the quotient. There's quotient, okay? So we're going to do that here, is called the quotient, okay? It is called the quotient. And we're going to underline that. There's underline for quotient. Oh, stop. There we go. And is read, so it's called the quotient. That's period, because this is the end of the sentence. The sign for the operation, is thus. And then in parentheses, we use, there are two of them that we could have, right? So we could have this symbol, right? Or we could also have the, why am I blanking? We have this symbol, right? That symbol right there. We also have, so we have this one, we have this one, we also have the sideways bar, right? To show the symbol, because that would be like 4 divided by 5 would be that, okay? Now, remember, once again, I apologize, this is weird, I get it, but no, it should not be backwards because this is a standard symbol. There we go. So thus is thus. It's either the bar, the symbol right here, or the diagonal slash, all right? Those are the three symbols that we use for division, okay? So the sign for the operation is thus, and it gives the three symbols, and is, here we go, and is written accordingly, colon. And now, as I said before, I then create a box, and in the box, I show. Now, once again, remember, these notes aren't for anybody. These are just for me. These are just showing the fleeting notes that I would then turn into English, okay? I'm just showing the process of how it would work. So in the box, we then have the symbol, and we have x over y. X over y. And it is read as the number by the number. So here below, it is written accordingly. And then below that, we go back to Gregg, which is and is read as. Now here's where it gets a little weird. It's x, which is that symbol, x by y. X by y. All right? Kind of weird, I get it, but once again, this is just the idea of the fleeting note. The fleeting note is the note that you would write quickly. This is an example of you would write this note quickly, and then after the fact, you would develop it into a full-fledged thought. Okay? So let's go ahead and read back over. We have done all. Oh, not yet. We have, do we have number 5? Yeah, so we have number 5 to do, and then I can go back and read through the different operations, okay? So let's do number 5, and then we will be able to go back through. Now, I just realized I'm a doofus because the Gregg needs to be backwards, but the Roman numerals, for Pete's sake, need to be in the normal direction, right? Remember, fleeting notes are only there to make it easier, but as far as the overall structure, that needs to be in the correct lineup. So this is number 3, and then the Gregg is to be read backwards or mirrored, and then number 2 goes over here like so, and then number 1 goes up over here and is set. Oh, it is set here. Number 1. Okay. There we go. So number 1, number 2, number 3, number 4, and now we're looking at number 5. Okay, so we'll shift number 5 back over here to this location, and then we start developing the idea from good old Augustus de Morgan. When two numbers or collections of numbers with the foregoing signs are the same, a certain symbol is put between them. Thus, that 7 and 5 make 12 is written in this way. 7 plus 5 equals 12. This is called an equation and is read 7 plus 5 equals 12. It is plain that we may construct as many equations as we please. Thus, and then he gives different forms and different operations, okay? So, what I'm going to do here is in order to turn this into a fleeting note, I need to put it in the context of The key word, notice what he's really focusing on is equation and equality, right? So what you would say, he's really wanting us to look at when two numbers or collections of numbers, he's looking at the results of operation. The result of operation, that's the key, okay? So what we're going to say is when one number, or when one number, and of course, once again, we start on this end, when one quantity, when one quantity possesses the same value, so we're going to go possesses, right? Is that possesses? We're going to go ahead and check that in the dictionary. And once again, in case anyone is interested, this dictionary that I'm using right here is below. It's below in the description. So you can play with it as you want or use it to your leisure. So possesses goes here. When one quantity possesses the same value as the result, résu of any of the, and he uses a good word, it's foregoing, yeah, of any of the previously listed would be another way to look at it. So previously, I believe that would be previously. Let's take a look. See if previously is a word, and it's not, so, but previous is, I know. There's previous. And yes, that is previous, but we need to make the V stroke just a little longer. So we're going to go any of the previously listed operations. So let's see, we have when one quantity possesses the value as the result. Hold on, I wrote that incorrectly. When one quantity possesses the value that is the same value, so let's go ahead and move this out over here, that is the same value as the result of any of the previously listed operations. The numbers are equal. The values are equal, okay? Listed operation. The values are considered equal. Let's put this here. Previously listed operations. The values are said to be equal. The values are said to be equal, and equal is equal, are said to be equal, And the comparison and compare, what is comparison? There we go. And the comparison is called an equation, is called and then equation. So let's look up equation. There we go. Is called an equation. We underline that. Okay, so let's go ahead and read back through. And we have when, let's read what we have so far. When one quantity possesses the value that is the same value as the result of any of the previously listed operations, the values are said to be equal, and the comparison is called an equation. And the comparison is called an equation. And that's a really important point, okay? It's the comparison itself that is the equation. The comparison is called an equation, and is read, it is read as the value equals the other value. Okay, so and is read. So we're going to put this here. We have undo. Put this here. Thus, the following, and by following we do thus the following, and here let's go ahead and check following down here. Thus the following, colon, we could do A plus B, where these are numbers, right? A plus B is equal to C, some value, right? A is some value, B is some value, and C is some value. A plus B is equal to C, or D times R is equal to E, where each of these are numbers. We could even have V times H minus Y is equal to F. Each of these are different variations, right? Each of these would then be, so thus the following, and then each of these forms would be when, so now here's the key. We would say when read would state, and then we do the three forms below. We would have A plus B, A plus B equals C. A plus B equals C. Our next one would be D. So this is D times, or D into, right? I think the term he uses is D into, yeah. So we have D into R, D into R equals E. D into R equals E. And then our final one is V into H minus Y. So you would say V, or just V, into H. And what is H in Gregg? I forget what H is in Gregg. Let's see. V into H. Would that be just the ch symbol with a dot over the top? I've never actually looked into that. Let's just out of curiosity, let's see what that is. Yeah, I know that that's the dot, but yes. Oh, I know what Gregg alphabet, I think, is what I'm looking for. The letters of the alphabet in Gregg. The letters of the alphabet in Gregg. There we go. Just looking at it. Yes, so what is H? H is the dot. Okay, it's the dot, which makes sense. Okay, so we'll go back over here, and we're just going to do H. 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 Okay, so B into, or V into H, V into H minus, so we're going to use minus again, right? Minus Y equals F. And F is, what is F just by itself? F is, yep, it's just the F symbol into F. Okay? So this would be, and that, if I'm not mistaken, that is the last part, right? Of, yes. Yes, so you can construct as many equations as you please. And so one thing I do want to note is we have the first one here, the second one is here, and the third one is here, right? When red would state A plus B equals C. D, and D I think is just the dis symbol, right? Pretty sure it is. D into, take a look here, D into R equals E. V into H minus Y equals F. Okay? So those are the forms. Those are the three words in Gregg. Okay? So we've got that. And that's pretty much it. It often becomes necessary. So now that's all we need for each of those. Those are the 5 operations. So let's go ahead and list them again. So we're going to go back up here and we're going to take a look at number 1, starting all the way from the top. So this is 23. Let's go ahead and read through 23. Okay, here we go. To reduce the wording for arithmetic operations, symbols are used to denote the processes. When 2 So here's our first one. Let's go ahead and do a little symbol right here so that we can denote that we're talking about a different thing altogether. So there we go. That's our symbol. That's where we're making a break. Okay? And now we go back here to our pointer and we say when two or more quantities are joined, the result is called the sum. The symbol is called the sum. The symbol of addition is known, and I'm pretty sure that's known, but I need to check it again. The symbol of addition is known, and that is correct. The symbol of addition is known as plus, and is denoted by. So we need to put this here. No, and is yeah, that's denoted. And is denoted by, this should be by. By, there we go. Go back over here. By the character of the cross, right? Which is plus. The plus. Plus is the Latin for more. It's the Latin for more. And that's the word more. Okay? And here's our second one. This is the second operation. When a quantity is removed from another quantity, the value that is left is known as the difference. And the symbol used to denote our or show the operation of this is subtraction is called, and I need to do this, put a little symbol of is called, there we go, is called minus, and is read as x minus y, which in Gregg would be x minus y. Here's our third symbol. So we've done two so far. When a quantity is taken a certain number of times, the result is called the product, and the operation is denoted thus: x or a into b, and that's a into b. Let's go ahead and put the little symbols under this so that we show we're talking about the names of the letters. A into b, and then below it says the symbol is known as a multiplication sign. Is known as a multiplication sign. Okay. Now we go down here to the fourth. Here we go. Fourth one. When you attempt to find how many of one number is in another number, this is called division, and the result of the operation is called the quotient. It's called the quotient. The sign for the, and let's make the 4 just a little smaller. The sign for, there we go, for the operation is thus: this symbol, or this symbol. In fact, let's go ahead and underline all of them. So it's this this symbol here, boom, that symbol, or that symbol right there. All of those would denote the sign of division. Okay, so this, or this, and is read and is written accordingly. X by y, and is read as x by y, x by y. Let's go ahead and underline these characters to show that we're dealing with capitals or dealing with the names of the notes. Okay, and I will be back in just a second, so Testing 1, 2, 3, testing 1, 2, 3. So I need to make sure I'm going to go ahead and fix my lighting because we've gotten dark. The sun is going down. Let's go ahead and increase the exposure. 1 level, 2. Nah, just 1, and then we'll bump up the gain a little bit. There we go. All right, so back at it, back at it. All right, so as I was reading through, these are all the fleeting notes, of course, and this is what you would then develop your ideas from. And once again, the concept of a fleeting note is that you don't want it to be in the same language as the original. You want it to be in your own form. Okay, so we're looking here at Augustus de Morgan. We're currently on the operations. We're looking at the operations of arithmetic, okay? And so we had just finished our x over y. So this was x by y. X by y is the way that you want to think about that as the form. And now we're looking at the fifth form. And so we're going to go ahead and read through that. Here is my takeaway. Here's my takeaway from his particular point that he makes in 5. When one quantity possesses the value that is the same value as the result of any of the previously listed operations, the values are said to be equal, and the comparison is called an equation. Thus the following, and then I list these, the following: A plus B equals C, D into R equals E, V into H minus Y equals F. And that's what each of these symbols below are stating. All of those are examples of equations. All of those are examples of equations, okay? Now what I want you to pay attention to is this line right here when I said that a value is equal to the result of an operation. It has to be equal to the result of an operation, okay? So that is everything to be taken away from the 23rd paragraph, and those are the forms, or those are the signs of arithmetic operations. There are 5 of them, right? Addition, subtraction. In fact, what I'll do is below, not in Gregg, I'm just going to review so we can remember the 5. So this is takeaway, thought, and these are the 5 operations. 5 operations. And those 5 operations are going to be addition, subtraction, to subtract quantities, to add quantities, to multiply quantities, to divide quantities, and I'm using that word quite deliberately there, to multiply quantities, to divide quantities, and to compare quantities. Comparison itself is an operation. Okay? Those are the 5 operations of arithmetic. It is to add, to subtract, to multiply, to divide, and to compare. Those are the 5 operations, the 5 basic operations of arithmetic. Everything else, as they say, is just commentary. So now, let's go ahead and take a look at 24, and let's see if we can develop a fleeting note from that, from 24. So we're going to drop a paragraph 24. As I said in the previous stream, one of the nice things about older books in general is the way that they structure the textbooks. They lay them out in such a way where all the paragraphs are numbered, and so to me it's easier to navigate the book, but be that as it may. So let's go take a look at 24. It often becomes necessary to speak of something which is true, not of any one number only, but of all numbers. For example, take 10 and 7. Their sum is 17. Their difference is 3. If this sum and difference be added together, we get 20, which is twice the greater of the two numbers first chosen. If from 17 we take 3, we get 14, which is twice the less of two numbers. The same thing will be found to hold good of any two numbers, which gives this general proposition. If the sum, so let's actually lay out this example because this one's a little bit tricky, okay? All right, so this is comparisons. So let's go through this. For example, let's take, and when he says let's take, we're just going to write that down here. Let's take 10 and 7. 10 and 7. Their sum is 17. Their difference is 3. Okay? If the sum and the difference be added together, if the sum and the difference be added together, we get 20, which is twice the greater of the two numbers first chosen, which is twice the greater of the two numbers first chosen. 20 is greater than twice the greater of the two numbers first chosen. If from 17 we take 3, so hold on, we'll write this. We don't have a symbol for greater yet, so what I'm going to have to do is I'm going to have to just use the word, so which is twice the greater of the two numbers. So we get 20, which is twice the greater, so 2 times, which is 2 times the greater of the two numbers. 2 times the greater of the two numbers. If from 17 we take 3, so if from 17 we take 3, we get 14, which is twice the less of the two numbers, okay? Which is, notice here, this is important, which is twice the less, of the two smaller numbers. The same thing will be found to hold true for any two numbers, which gives this general proposition. If the sum and difference of two numbers be added together, the result is twice the greater of the two. If the difference be taken away from the sum, the result is twice the lesser of the two. If then we take any numbers and call them the first number and the second number, and let the number be the greater, we have first number plus second number plus first number minus second number is equal to twice the first number. The first number plus the second number minus, so the addition of the two numbers minus the difference of the two numbers is going to be equal to the second number. Well, that's really interesting, okay? Any computations which occur in this may be found on the fingers or with counters, okay? And counters, he means, if you're going to use counters, then that would be your abacus, which I'm not going to get into right now. But what is the takeaway from this particular idea? So 8 minus 2 plus 1 times 1ii signifies that 2 plus 1 must be taken twice times, and the product must be subtracted from 8. In the same manner, any result made from two or more numbers, which is true, whatever numbers be taken, may be represented by number second, number so on and so forth, and stand for, and by the signs in 23. But this may be much shortened for as first number, second number, so on, may mean any numbers, the letters A and B may be used instead of these numbers, and it may now be collected that A and B stand for two numbers, provided only that A is greater than B. Let twice A be represented by 2A and twice B by 2B. Then it lays out the equation, okay? All right, so what's that takeaway? What is the takeaway from 24? Well, it's a very interesting concept, which, to be honest, is not necessarily known that much, and that is that, let's go ahead and lay it out here. So the sum and the difference of two numbers, if the sum and the difference of two numbers are added, the result is twice the greater of the two, or is 2 times the greater of the two numbers. If the difference be found between the sum and the difference of the two numbers, then it will be equal to twice times the second number. Twice times the second number. Very interesting. Very, very interesting. He then goes on to talk about the fact that you can use variables. Okay? So a plus b minus b is equal to 2a, and a plus b minus a minus b is equal to 2b. This will be explained still further as follows, okay? So 24, the takeaway from 24 is, if we were to write it out, the takeaway from 24 is that if a number, actually, let's go ahead and change the ordering of this idea, okay? So we can say, which we've already been using this concept earlier, but we'll do it now, and we'll say that if operations, if arithmetic operations are universally true for all numbers, then certain signs drawn from the alphabet alpha, I think isn't it just ALF? Drawn from the alphabet. Let's go ahead and take a look. Drawn from the alphabet, yep. Drawn from the alphabet may be used in place of explicit numbers. Okay. May be used in place of explicit numbers. Okay, so let's go ahead and read back over that sentence. If, let's make F just a little bit smaller. Here we go. If arithmetic operations are universally true, let me go ahead and check universally. So universally does require, oh, it's E universally, so let's fix that. Here we go. If arithmetic operations are universally true for all numbers, then, and that looks like a them, so we'll fix that. Then, there we go. Then certain signs drawn from the alphabet may be used in place of explicit numbers. And then for example, so we have, for example, A plus B. Okay, for example, A plus B, where A and B are numbers, are considered to be numbers. Where A plus B, where A and B are part of the set, are one of the valid numbers. Let me check valid. Where A and B are one of a valid range or valid set. Valid, check that. Yep, that's valid. So we do need to have the E are one of the valid numbers. Okay. So that's the takeaway, is we go back here, we say if arithmetic operations are universally true for all numbers, then, and that's not all numbers, but because I know there are other numbers which, we won't get into. We won't get into those. We're just going to imagine that we're only talking about the natural numbers, what are considered natural numbers, okay? Later on, we'll flesh that out. Are universally true for all numbers, natural numbers, then certain signs drawn from the alphabet may be used in place of explicit numbers. For example, A plus B. A and B are where A and B are one of the valid numbers, okay? Since that's the case, we can use our symbols instead of explicit numbers. And that's what he's saying here when he says, notice that A and B, come on, oh, my pen is just, is highlighting. When he says, by this may be much shortened, for as second number may mean any numbers, the letters A and B may be used instead of these words, and it must now be collected that A and B stand for two numbers, provided only that A is greater than B. And then let twice A be represented as 2A and twice B by 2B. The equations then read. So what I'm doing is I'm first establishing the case that we are allowed to use alphabetical symbols to stand for numbers, okay? Nowadays we call those variables, but for right now we don't have to use the terminology of variables. We just say that an alphabetical symbol stands for a valid number. An alphabetical symbol stands for a valid number, okay? If this is the case, now let's actually go into, we're going to greatly shorten what he was saying through here, okay? Which is, it's an interesting concept, okay? I don't know if he gives the name for it or not, but let's go ahead and lay it out here. We're going to drop a little symbol here to show that we're dealing with a new concept, okay? A paragraph marker would work as well, but that little symbol right there is going to be perfectly adequate. So what do we have here? We have let, ready? Let A, and by A I'm going to do, we're going to see switching back and forth, so I apologize. Let A and B stand, and ST in stand. Let A and B stand for two numbers where A is the greater of the two numbers. Now what's interesting is, so he's talking about this idea of greater and lesser, but he hasn't even introduced the concept of the greater than lesser than signs. So I'm not going to do that here, but just know that what he's talking about is I'm just going to do a side note, okay? Side note, and I'm going to switch over to English here, or to orthography. Side note, okay? A is greater than B. A is greater than B, okay? So let's go back. Let, and this is here, we'll switch this to let. Let A and B stand for two numbers where A is the greater of the two numbers. Then the following is true. Then the following is true, okay? Then, comma, the following is true, colon. The sum of A and B, when added, let's give ourselves a little bit more room here. When added to the difference of A and B will result in twice times A. It will result in twice times A. Okay? It will result in twice times A. Pretty interesting. Okay, those are letters, by the way, right? A, B, A, B. So it will result in twice times A. And we can lay that out as in this particular form. Once again, in the English, we have the sum of A and B added to the difference of A and B will result in 2 times A. And that's what's meant when I say that the sum of A and B, when added to the difference of A and B, will result in twice times A, 2 times A. And that's here, A plus B plus A minus B is equal to 2A. Okay? And now, conversely, if the sum of A and B is, no, if the, we're going to swap the order here. If the difference of A and B is taken if the difference of A and B is taken from the sum of A and B, the result is twice times B, where B is the lesser. And let's look up lesser. Is the lesser of the two values. Okay? And how do we lay this out in mathematical language? This is laid out in mathematical language as saying the sum of A and B minus, or the difference of A and B is equal to 2 times B. Okay, so those are two equations which are really important for us to remember. The sum of two numbers, when added to the difference of two numbers, will result in twice times the larger of the two numbers. The difference of the sum of two numbers and the difference of the two numbers will result in twice times the smaller of the two numbers. Okay, so those are two equations which are going to be pretty useful to remember, okay, because there might be cases, there will be cases where it's going to be useful to know that relationship, okay? And does he give a name for this? Not really. But what he does here, so now once he's laid out these, so we have a plus b plus a minus b is equal to 2a, and a plus b minus a minus b is equal to 2b, okay? Now, with this being said, and it looks like we've gone dark again, so we'll need to go ahead and increase the light of the video, as we do this way too often. So let's do video, and let's bump up our exposure. There we go. Exposure's gone up, and gain goes up slightly, and then brightness goes up as well. There we go. All right, so now with this, we'll be able to finish out the remainder of the video. Okay, so there we go. Let's go ahead and minimize this right over here. And we start back in. So now, that really is the takeaway from the 24th. That's the takeaway from the 24th paragraph. So if we read back over it, let's read it in context. If arithmetic operations are universally true for all numbers, or for a range of numbers would be another way to say it, for all numbers, then certain signs drawn from the alphabet may be used in place of explicit numbers. For example, A plus B, where A and B are one of the valid numbers, where a and b are one of the valid numbers, okay? Now here's the second part of that paragraph. Let a and b stand for two numbers, where a is greater, where a is the greater of the two numbers. Then, uh, then the following is true. The sum, and the sum should be just a little smaller. Grab that. There we go. The sum of a of a and b, when added together, when added to the difference of a and b, will result in twice times a. And this written out mathematically is labeled thus: a plus b plus a minus b is equal to 2a. And then here's our second portion. If the difference of a and b is taken from the sum of a and b, then the result is twice times b, where b is the lesser of the two values. And this written in mathematical symbols is a plus b minus a minus b. In other words, the difference of the sum of a and b and the difference of a and b is equal to 2b. Okay, so there we go. That is pretty much everything that is taken from 25 or from 24, and now we follow up with 25. We follow up with 25. Let's go get this lined up here, and we start now. Okay, 25. Suppose a number of sealed packets marked A, B, C, D, etc. On the outside, each of them contains a distinct but unknown number of counters. As long as we do not know how many counters each contains, we can make the letter which stands to each stand for its numbers, so as to talk of the number A instead of the number in the packet marked A. And because we do not know the number, it does not therefore follow that we know nothing whatever about them, for there are some connections which exist between all numbers, which we call general properties of numbers. For example, take any number, multiply it by itself, and subtract 1 from the result, and then subtract 1 from the number itself. The first of these will always contain the second exactly as many times as the original number increased by 1. Take the number 6. This multiplied by itself is 36, which diminished by 1 is 35. Again, 6 diminished by 1 is 5, and 35 contains 5 7 times, that is 6 plus 1 times. This will be found to be true of any number, and when proved, may be said to be true of the number contained in the packet marked A, or of the number A. If we represent A multiplied by itself, AA, we have by AA minus I, or minus 1, over A minus 1 is equal to A plus 1. Okay? Once again, this is another really good equation. You really can't see it now, but it does have value in further applications. It's just one of those things that you memorize and you have stored, okay? So we go back up here, and let's go ahead and start. Let's see if we can make a fleeting note from this particular paragraph, okay? Now, Remember that we had already spoken about this idea of being able to give letter names, alphabetical names, to particular numbers, right? So what we're going to do here is we're just going to elaborate on it a little bit more. And the elaboration, it says, as long as we do not know how many counters each contains, we can make the number which belongs to it stand for its number, so as to talk of the number A instead of the number in the packet marked A. And because we do not know the numbers, it does not therefore follow that we know nothing whatever about them, for there are some connections which exist between all numbers, which we call general properties of numbers. Okay? So, what we're going to do in 25 is we're going to perform the same operation that we did in 24, and that is we are going to speak of the qualities or the fact that we can look at general properties of numbers. Okay, so we're going to say that a number may be spoken of. So here we go. A number may be spoken of and spoken should be, I think it's just SP and then in. Let's go check that out and see. A number may be spoken of SPK in may be spoken of with no knowledge of its explicit quantity, its explicit or certain quantity. Okay? All right, so that's what's meant here when it says that we do not have to know the number of counters, and that's quantity. We don't have to know the quantity of the number. All we need to know is that it is a number, right? As long as it belongs to the set of counters. If it could potentially have a counter, then that's what we're talking about, okay? We can make the letter which belongs to it stand for its number so as to talk of the number A. And then, so if we can do the certain here, fix this up a little. There we go. Certain quantity. A number may be spoken of with no knowledge of its explicit or certain quantity. The name of this number, and I think it's num, isn't it? Or is it num? I forget. Let's go check. It is num, yep. The name of this number becomes, so let's go becomes the important considering, let me check and see if that's considering. Yep. The becomes the important considering factor. And the general, let's give ourselves just a little bit more room, considering factor, right down here, comma, and the general and the general, I believe, or no, it's just gen. And the general properties of numbers. And it is then considered in the context of the general properties of numbers. And then, there we go. And then it is investigated, and then it is, we could use considered again, or it is thought of would work as well. Thought of with respect, respect. Is that just RES? Let's see what respect is. RES, that's right. With respect to its general properties, to its general properties. Go check that out here. Nope. There we go. Property. With respect to its general properties. And properties. Okay? So what's the takeaway there in 15? It says that, go ahead and write this out here. Where's our highlighter? A number may be spoken of with no knowledge of its explicit or certain quantity. Then the name of the, so we need to fix this here. Then the name of the number becomes the important considering factor, and then it is thought of with respect to its general properties. Okay? A number may be spoken of with no regard with no knowledge of its explicit or certain quantity. Then the name of the number becomes the important considering factor, and then so we can get rid of then, and it is thought of with respect to its general properties. Okay, so then once we have that form, once we have that understanding, we are talking about another case. It's another interesting concept of numbers. So first of all, he introduces the idea of that we can speak of the number by its name instead of the number in the packet. And we are looking at, there are some connections which exist between all numbers, which we call the general properties. These are the general properties of numbers, okay? Now, what is one example? For example, take any number. Let's take A, for instance, right? That's the form he gives. Take any number. Multiply it by itself and subtract 1 from the result. And then subtract 1 from the number itself. Okay? And then subtract 1. The first of these will always contain the second exactly as many times as the original. and then subtract 1 from the number itself. Okay? And then subtract 1 from the number itself. The first of these will always contain the second exactly as many times as the original number increased by 1. So that's what it means here. The first of these will always contain the second exactly, okay, as many times as the original number increased by 1. So if we have a plus 1, okay, and we say that we take the multiple a times a minus 1 divided by a minus 1, this is going to be equal to a plus 1. A times a minus 1 over a minus 1 is equal to a plus a, or a plus 1. Once again, this is another form that we want to keep in mind, okay? This is really important. Now, we're not talking about powers just yet, but we can just write them as next to each other, okay? For example, take any number, multiply it by itself, and subtract 1 from the result, and then subtract 1 from the number itself. The first of these will always contain the second exactly as many times, right? And that's the idea. It will contain exactly as many times as the number with 1 added. So for example, let's try it with 6. Let's take the number 6, okay? Multiplied by itself is 36. So let's take a, let's do an example. Here's an example. A is equal to 6. Then if we substitute any time we have a, we end up with 6 times 6 minus 1 all over 6 minus 1, and then 6 plus 1. Okay? Remember, we can see that we are substituting anytime we have a, we would put a 6 in its place. So if we then fill this out, we end up with 36 minus 1 all over 5, and then we have 7. So then we end up with 35 over 5 equal to 7, which is 7 equal to 7. As you see, that works itself out, okay? So that would be, this should be a times a, but the sign is unnecessary. It is used with numbers. He has a little note here where he says that the only time that you need to have the multiplication sign is when you're dealing with explicit numbers. If you're dealing with implicit numbers, then, or just the sign of the number, then you don't need to have the multiplication sign. So just two numbers next to each other, if they are implicit, which in this case a would be an implicit number, then it is understood that when they're next to each other, that is the sign of multiplication. Okay? All right? So that really is the takeaway from, that's the takeaway from 25. First of all, it's just a little bit of a reiteration of how you can think about numbers devoid of their explicit value or explicit quantity, and then but the properties of numbers still pertain. Okay, that's the takeaway from 25. And then in 26, let's go ahead and grab that. The takeaway from 26. When, therefore, we wish to talk of a number without specifying any one in particular, we use a letter to represent it. Thus, suppose we wish to reason upon what will follow from dividing a number into 3 parts, without considering what the number is or what are the parts into which it is divided. Okay? So let A stand for the number, and B, C, and D for the parts into which it is divided. Then, by our supposition, A is equal to B plus C plus D. On this we can reason and produce results which do not belong to any particular number, but are true of all. Thus, if one part be taken away from the number, the other 2 will remain. Okay? A minus B is equal to C plus D. If any part be doubled, then the whole part will be doubled, or 2a is equal to 2b plus 2c plus 2d. If we diminish any of these parts as d by a number x, we diminish the whole number just as much. A minus x is equal to b plus c plus d minus x. Okay? And so that is pretty important right there. How are we going to differentiate, no pun intended, how are we going to figure this one out, this 26? Well, ultimately, it borrows from the previous paragraph, which stated that we can look at the general properties of numbers, okay? And the general properties of numbers pertains to all of the operations. What are all the operations? Let's go ahead and draw a paragraph here on 26. So on 26, what are the operations? Let's review. What are the operations of arithmetic? They are addition, they are subtraction, they are division, they are division, they are multiplication, and they are comparison. They are comparison. And that's the five, these are the five operations of arithmetic. Addition, subtraction, hold on, here we go. Addition, subtraction, division, multiplication, and comparison. Okay? Now, remember what De Morgan was just saying here is that you don't need to know the explicit. So I'm just going to do this in pure English because we haven't really developed a fleeting thought yet. You don't need to know the explicit value of a number. The explicit value of a number does not need to be known. And by explicit, I mean its numerical value. The explicit value of a number does not need to be known. Does not need to be known when observing the general properties. When observing general properties. Okay? So you see that that's really important. The explicit value of a number does not need to be known when observing general properties. And then we can speak of it. We speak of it by its name. Its name. And we assign a name. Usually we assign a name from the alphabet. Names are usually drawn from the alphabet. Usually drawn from the alphabet. Okay, so that's the key right there. Names are usually drawn from the alphabet. Now, here's the important part. Here's the clincher. And really, this is the part that trips pretty much everybody up. The idea, you know, a lot of people can understand x plus y, or x minus y, or x divided by y, or x times y, right? We understand these, right? We have x plus y, x minus y, x divided by y, or finally x times y. Now remember, if we're talking about the name of the number in its general properties, we don't have to include the multiplication symbol. We can just have the two numbers next to each other, and it's always understood that we are dealing with multiplication. Now here's the interesting thing, okay? The one symbol that we haven't discussed yet, we have multiplication, subtraction, division, and multiplication. Sorry, I meant addition. The one operation is comparison. As soon as we drop a comparison symbol, this is still an arithmetic operation. This is still an arithmetic operation, okay? Which means that whatever happens on one side can be done on the other because we're comparing. The thing about comparison is we need to make sure that things are balanced. Things are balanced. It's almost like the comparison symbol is almost like the scales, right? So if you've seen the old time scales where you've got a base, right, and it comes up here, you have a scale here, comes up to this point, and you have a balancing point, and then you have an arm coming off of both of these, and the arm then has a basket, right, with a little bowl on one side, and there is a basket or a little bowl on the other side. And what you do is whoop, there we go. So this is also called a Libra, right? A Libra. And Libra is scales, which is why, for instance, that's why it's one of the zodiac signs. You probably have seen this before. You know the zodiac here, which it's symbolizing. That one would be symbolizing the Libra, or the scale. Okay? That is what the equal symbol is. The equal symbol is a Libra. The equal symbol is a Libra. This means that whatever you do on one side, it has to be done on the other side, okay? What this means is that let's say we have y, or in his instance we have a, is equal to b plus c plus d, okay? This would be a comparison. As long as b plus c plus d is equal to a, as he says here, we're looking at the division, right? Suppose we wish to reason upon what will follow from dividing a number into three parts. So the number a has been divided into b, c, and d. And that would be laid out thus. Okay? These are the general principles. We don't need to know the explicit value because we're looking at the general principles. And we said that some number a has been divided into b, c, and d parts. And the addition, if you were to put them back together, then you would end up with the resultant sum, which would be a. The part b plus the part c plus the part d would equal a. Okay? On this, we can reason and produce results which do not belong to any particular number, but are true of all. Thus, if one part be taken away from the number, the other two will remain. Once again, remember our Libra example. Remember how essentially we are talking about equality. We want this to be equal. So, if one part be taken away from the number, the other two will remain. So let's imagine that we took b away. Well, we would say that the b has been taken away from a, but the other two remain, right? Because we're talking about parts. We're talking about the parts of a number. So even though b has been taken away, one of the parts has been taken away, we still end up with equality. B was taken away from A, so therefore B was taken away from the three groupings, but C and D are still there. Okay? If each part be doubled, the whole number will be doubled. Or, right? So this is an example of where we took one away, we took B away, and we took it away from A as well. So it's A minus B is equal to C plus D. Once again, remember, we are talking about the final operation of arithmetic, which is equality. Comparison. Comparison, we're comparing values. We're comparing a total sum with the result of an operation. All right? So this is one instance. Now we have another one. What if we have 2, right? What if we want to multiply everything by 2? Well, we have twice times a, and if we're looking at the three parts, then it's also twice times the first part, plus twice times the second part, plus twice times the third part. Twice times a is equal to twice times b plus twice times c plus twice times d. If we diminish one of the parts as d by a number x, we diminish the whole number just as much, right? So looking back at a being split into the three parts, b plus c plus d. if we want to take a little bit away from one of the numbers, we have to take it away from the whole. Once again, because we're talking about the Libra. We're talking about the balancing of the scales. Whatever we do to one has to be done to the other, right? What we do in one, we have to do in the other in order to keep the scale balanced. That's what an equation is. An equation is the balancing of both halves of the scale. So, to use the example here, if he says if we diminish one of the parts as d by a number x, we diminish the whole number just as much. So that would look like the whole number, which is a, we would have to take an x portion away in order to also take the x portion away from d. What you do to the parts, you must do to the whole. And that is the end. So that is the end, and wow, that's actually perfect timing because I have 6 minutes left on my clock. And that is the end of the first section. Very nice, very nice. So that was actually quite fun. What did we cover in the last few minutes? Let's go ahead and go back over what we covered. And I will have to make a fleeting note for 26 because that is a really fundamental, I mean, to be honest, that point in paragraph number 26, upon that point, everything else is based. Everything else in arithmetic, in algebra, in trigonometry, in any of the branches of mathematics, calculus, all of that it boils down to the idea of balance. What you do on one side, you can do on the other side, okay? So super important, super important. So what did we cover? We started back in, let's see here, where were we? The set of numbers. We had talked about the fleeting note. This is where we started. In fact, let's go ahead and drop the date so that so that we pay attention to that point. So this was today's date, and it was, let's go ahead and put this here. So this was today's date. This is August 11th, 2026, okay? August 11th, 2026. And so what was the fleeting note here? If we just read back through, then we have, where's our little pointer? Let's see if I can still read it. We have higher value numbers are specified by a series of symbols where every sign is one of a fixed set of characters that increases at a rate of, oh, these are the linked signs, that's right, that increase at a rate of the written value times a factor of the taught count of the total count of attention, the total count of the total count of items in the set. And in this case, we dealt with the set of numbers, which was 1 through 9, right? And 0. So there were 10 symbols, and that was the set number. So therefore, if we're looking at a number and we're reading it out, we have our place value. Essentially what we were talking about was place value. We have the eighth position, B, C position, D, E, and F. First, second, third, fourth, fifth, and sixth. And A had a factor of 0, right? B had a factor of 1. C had a factor of 2. It was 2 times the set number. D had a factor of 3. It had 3 times the set number. E had a factor of 4. 4 times the set number. F had a factor of 5 times the set number. Okay? And then the fleeting note here was every position in the linked system of numeration is given a name. The first position bears the name of units place, and every successive position is given the name of the associated factor. So that is where we get the units or the ones place. It's the units place, the tens, hundreds, thousands, 10,000s, 100,000s. Okay, so that was the takeaway from 3. And then we have, so we have A as units, B as tens, C is hundreds. Okay, and then here is our fleeting note for the fourth point, and it says that in linked numeration, positionality is of ultimate importance. Symbols note symbols known as cipher, a symbol known as a cipher, which has no inherent value in itself, must be used to shift symbols that do possess value and list them in the correct position. So my time has ended now, but that was, we talked about ciphers, we talked about the need for positionality, we talked about different methods of parts, right, based on position. So the old British method was the pound, the shilling, and the pence, right? And 1 shilling was 12 pence, and 1 pound was 240 pence, and 1 pound was 20 shillings. And then we talked a little bit about US currency, and so on and so forth. Well, with that, this video is done. I am through for tonight, so thank you very much for watching. I hope that you have a wonderful evening, and that at least it was somewhat entertaining or interesting. I know that this particular approach, especially as pertains to something as seemingly banal as arithmetic, it seems like it would be a little bit too much. Like, why am I focusing so much attention on this particular domain? But believe me, the information that is being presented here at the level of arithmetic is absolutely foundational. There is a world of knowledge that is being laid out here by Augustus de Morgan, and everything that you then study in the world of algebra, in trigonometry, in geometry, in calculus, in linear equations and differential equations. Every single branch of mathematics is built and focused here at this level of arithmetic. It is truly foundational. It lays groundwork. And so with that, I'm going to call it an evening. Thank you so much, and I hope that every one of you had a wonderful day and were able to accomplish everything that you set out to accomplish. So, until we meet again, have a wonderful evening. Bye-bye.